Okay, so just to finish up what we were talking about today in class. So we were talking about tensions in rope, strings, and cables. We came up with the definition of tension, the magnitude of a force exerted on or by cable, string, rope. Each section of the cable exerts a force equal to the one that it experienced on the adjacent section, passing it down the cable. We had three assumptions. One, that the mass of the rope was so small it did not significantly affect the motion and could be ignored, and that's good as long as you pick your rope wisely. The second one, the tension is the same at every point, and that is true as long as the rope is uniform and not damaged. And the third one, if the rope or cable passes over a pulley, the direction of the force will change but not the magnitude, and that is a valid assumption as long as the pulley is assumed to be frictionless and its mass negligible. So we're going to start with easy ones before we get to multiple masses. And easy ones are like if you have an object, and maybe that object is an elevator, and you're going to pull upward with some force tension, and gravity's going to act downward. And maybe with all the people on the elevator, there's 3,200 kilograms here, okay? And so the question would be, what's the tension? Oh, the elevator is accelerating upward. So A is 0.55 meters per second squared upward. So the question would be, what's the tension in the rope? Well, this time you just do sum of the forces in the y, and it's not going to be zero. So it'll be Ft minus Fg equals MAY, and you're solving for Ft. So Ft will just equal MAY plus Mg. And now you fill your numbers in. 3,200 kilograms, 0.55 meters per second squared, plus 3,200 kilograms times 9.81 meters per second squared. And when you do this and type it in, you should get 33152 newtons up. Works out to be positive. Now, just one little point. Sometimes when people do this, they want to put their 9.81 in as negative. But we already called Fg negative here. So you can't put it in negative again, right? Like, so we already allowed for the fact that Fg was going down here by calling it negative. So now put your 9.81 in just as its magnitude, not its direction, because we looked after the direction right there. Part B might say, so this would be part A, it's accelerating upward. Part B might say, what if the elevator was accelerating downward? So A is equal to 0.55 meters per second squared down. So you would do exactly the same thing. Sum of the forces in the y is equal to MAY. And now you have a choice. Which way do you want to call positive? If you want to call the direction of motion positive, then the sum of the forces would become Fg would be positive, it's going down. Ft would be negative, it's going up, is equal to MAY. And you're solving for Ft. So it would become Mg minus MAY is equal to Ft. Okay? And then mg, so that 3,200 kilograms times 9.81 meters per second squared minus 3,200 kilograms. And we call down positive, so this goes in as 0.55 meters per second squared. And this should give me Ft. And you would get an Ft of 29632 newtons down. Now, if I screwed you up, let me do it by calling up positive. So A is still going to be 0.55 meters per second squared, so this is with down positive. And this is with up positive. Okay? So this is still going down. So if we do up positive, then when we do our sum of the forces, it'll be Ft minus Fg, because we're calling up positive, equals MAY. We're solving for Ft, so it becomes Ft equals MAY plus Mg. So Ft equals the 3,200 kilograms. But the A is down, so it has to go in as negative 0.55 meters per second squared plus the 3,200 kilograms times 9.81 meters per second squared. And so in this spot, the negative comes about because of the direction. In this spot, it's still with the direction, but it's actually on the A itself. Okay, and you still end up getting 29632 newtons. Works out to be negative in this case. No, it works out to be positive. I said down there, but it's up. I must have been falling asleep. It works out to be positive, so it'll be up. So those are simple elevator problems, not going to be on the test, but will be your homework the night of the test, okay, after you finish the test. A couple other little things, because I want to look at, we're going to start looking at pulleys, and so this will just help us when you come back the day after the test, okay? So this instrument, this thing right here, is brilliantly called the Atwood machine. Okay, its name is fancier than what it actually is. And if this is M1 and this is M2, which way, and this is the pulley, which way these blocks will move when I release them totally depends on whether M1 is bigger or M2 is bigger. So this will be FG1 acting this way, this will be FG2 acting this way. It's like they're in a tug of war. Now there is an FT1 acting up here and an FT2 acting up here, but remember all the pulley does is change the direction of the force. So FT1 will be equal to FT2, right? They're just opposite. Equal in magnitude but opposite in direction. We could draw this system like this. This system that's moving on a pulley is exactly the same as if we drew it in a straight line where M2 was pulling this, FG2 was pulling this way, and FG1 was pulling this way. And in here will be the FTs canceling each other out because they're just pulling opposite each other and they're equal. So what's going to determine if the system moves is these two guys. They're called the external forces. Okay? And external forces are the forces that act on the system from the outside, like gravity, and they determine the motion of the system. So they act on the system from the outside and they determine the motion of the system. Gravity and friction are the two big external forces. We also have internal forces. And internal forces are forces that act between the objects in the system. So this whole system is like M1, M2, and the pulley, which is massless and frictionless, so we can ignore it. So the internal forces are forces that act between the objects of the system, and they do not affect the motion of the system. So they act between the objects, like these FTs, and they don't affect the overall motion of the system because they really end up canceling each other out when we're looking at the whole thing. Okay, so when you want to solve for the system, when you want to solve for the tension, you have to look at just one object or the other. And I'll do an example of that on the day after the test. Okay, for right now, internal motion and internal forces and external forces. One other thing, this time, now when we get into multiple masses, you have to call the direction of motion positive. You can't just say up is positive anymore, right? Like if M1 is 20 kilograms and M2 is 30 kilograms, well then M2 is going to move downward, so down on this side will be positive, but M1 is going to move upward, so down on this side will be negative. So now you can't just say up is positive, you have to say M1 moving up is positive and M2 moving down is positive. And that's why sometimes it's easier to draw it in a straight line. Remember, the pulley only changes the direction. So then this way would be positive if M2 was bigger, and this way would be negative. Okay, so again, we'll come back to this the night of your test. The homework the night of the test will be on some of this, well, it'd actually be on this straight line stuff, and then the next day will be the Atwood. Okay? So now get busy on your other homework.